So, okay, happy ending. We are done, and we now have the correspondence. Are we done? Well, not quite. Okay, why are we not done? Because the analogy I gave you requires a particular hypothesis in mind. I told you that the red and green marbles correspond to the agreement between H and the target function. So when you tell me what H is, you dictate the colors here, right? All of these colors. This is green, not because it's inherently green, not because of anything inherent about the target function. It's because of the agreement between the target function and your hypothesis H. Okay? That's fine. But what is the problem? Well, the problem is that I know that for this H, nu generalizes to mu. You're probably saying in your mind, yeah, but H could be anything. I don't see the problem yet. Okay? Now, here is the problem. What we have actually discussed is not learning, it's verification. The situation as I describe it, you have a single bin and you have red and green marbles and this and that corresponds to the following. A bank comes to my office, we would like a formula for credit approval. Okay, and we have data. So instead of actually taking the data and searching hypotheses and picking one that, like the perceptual learning algorithm, here is what I do that corresponds to what I just described. Okay, you guys want a linear formula? Okay, I guess the salary should have a big weight, let's say 2. The outstanding debt is negative, so that should be weight minus 0.5. And years in residence, okay, are important, but not that important, so let's give them a 0.1. And let's pick a threshold that is high in order for you not to lose money. Let's pick a threshold of 0.5. Sitting down, improvising an H. Okay? Now, after I fix the H, I ask you for the data and just verify whether the H I picked is good or bad. That I can do with the bin. Because I'm going to look at the data. If I miraculously agree with everything in your data, I can definitely declare victory by Höfting. But what are the chances that this will happen in the first place? I have no control over whether I will be good in the data or not. The whole idea of learning is that I am searching the space to deliberately find a hypothesis that works well on the data. In this case, I just dictated a hypothesis, and I was able to tell you for sure what happens out of sample. But I have no control of what the news I'm going to tell you. You can come to my office, I improvise this, I go to the data, and I tell you I have a fantastic system. It generalizes perfectly, and it does a terrible job. That's what I have, because when I tested it, new was terrible. So that's not what we are looking for. What we are looking for is to make it learning. So how do we do that? So no guarantee that nu will be small, and we need to choose H from choose the hypothesis from multiple H's. That's the game. And in that case, you are going to go for the sample, so to speak, generated by every hypothesis, and then you pick the hypothesis that is most favorable, that gives you the least error. Okay? So now, okay, that doesn't look like a difficult thing. It worked with one bin. Maybe I can have more than one bin to accommodate the situation where I have more than one hypothesis. Looks plausible. Okay? So let's do that. We will just take multiple bins. Okay? So here is the first bin. Okay? Now you can see that this is a bad bin. So that hypothesis is terrible. Okay? And the sample reflects that to some extent. Okay? But we are going to have other bins. So let's call this something. So this bin corresponds to a particular H. And since we are going to have other hypotheses, we are going to call this H1 in preparation for the next guy. The next guy comes in, and you have H2. And you have another mu2. This one looks like a good hypothesis, and it's also reflected in the sample. And it's important to look at the correspondence. Okay? If you look at the top red point here and the top green point here, this is the same point in the input space. It just was colored red here and colored green here. Why did that happen? Because the target function disagrees with this H, and the target function happens to agree with this H. That's what got the color green. And when you pick a sample, the sample also will have different colors because the colors depend on which hypothesis, and these are different hypotheses. Okay? That looks simple enough. So let's continue. and we can have m of them, okay? I am going to consider a finite number of hypotheses just to make the math easy for this lecture. And we're going to go more sophisticated when we get into the theory of generalization. Okay, so now I have this. This is good. Now I have samples, and the samples are here different. And I can do the learning. And the learning now abstractly is to scan these samples, looking for a good sample. And when you find a good sample, you declare victory because of Höfding, and you say that it must be that the corresponding bin is good, and the corresponding bin happens to be the hypothesis you chose. So that is an abstraction of learning. Okay? That was easy enough. Now, because this is going to stay with us, I'm now going to introduce the notation that will survive with us for the entire discussion of learning. Okay? So here is the notation. Now, we realize that both the mu, which happens to be inside the bin, and nu, which happens to be the sample frequency, in this case the sample frequency of error, both of them depend on h. So I'd like to give a notation that makes that explicit. So the first thing, I'm going to call mu and nu with a descriptive name. So nu, which is the frequency in the sample you have, is in sample. That is the standard definition for what happens in the data that I give you. If you perform well in sample, it means that your error in the sample that I give you is small. Okay? And because it is called in sample, we are going to denote it by E in. Okay? I think this is worth blowing up because it's an important one. Okay? So this is our standard notation for the error that you have in sample. Okay? Now we go and get the other one, which happens to be mu, and that is called out of sample. Okay? So if you are in this field, you guess what matters is the out of sample performance. That's the lesson. Out of sample means something that you haven't seen. And if you perform out of sample on something that you haven't seen, then you must have really learned. So that's the standard for it, and the name for it is E out. Okay? Okay, so with this in mind, we realize that we don't yet have the dependency on H, which we need. Okay? So we are going to make the notation a little bit more elaborate by calling E in and E out, calling them E in of H and E out of H. Why is that? Well, the in-sample performance, you are trying to see the error of approximating the target function by your hypothesis. That's what E in is. So obviously it depends on your hypothesis. So it's E in of H. Someone else picks another H, they will get another E in of H of their H. Okay? Similarly, E out, the corresponding one, is E out of H. Okay? So now what used to be nu is now E in of H. What used to be mu inside the bin is E out of H. Okay? Now the Höfding inequality, which we know all too well by now, said that. So all I'm going to do is just replace the notation. And now it looks a little bit more crowded, but it's exactly the same thing. Okay? The probability that your in-sample performance deviates from your out-of-sample performance by more than your prescribed tolerance is less than or equal to a number that is hopefully small. Okay? And you can go back and forth. There's a new mu, or you can go here and you get the new notation. Okay? So we are settled on the notation now. Now let's go for the multiple bins and use this notation. Okay. So these are the multiple bins as we left them. We have the hypothesis H1 up to Hm, and we have the mu1 and mu_n. And if you see 1 to m, again, this is a disappearing nu, the symbol that the app doesn't like. Okay? But thank God we switched notation so that something will appear. Okay? Yeah, okay. So right now, that's what we have. Every bin has an out-of-sample performance, and out-of-sample is out of sample. Okay? Okay, so this is the sample. What's in it is in sample. What is not in it is out of sample. And the out of sample depends on H1 here, H2 here, and Hm here. And obviously, these quantities will be different according to the sample, and these quantities will be different according to the ultimate performance of your hypothesis. Okay? Okay, so we solved the problem. It's not verification. It's not a single bin. It's real learning. I'm going to scan these. So that's pretty good. Are we done already? Not so fast. Okay, what's wrong? Okay, let me tell you what's wrong. The Hövding inequality that we have happily studied and declared important and all of that doesn't apply to multiple bins. What? Okay. You told us mathematics and you go read the proof and all of that, and what, are you just pulling tricks on us? What is the deal here? Okay. And you even can complain. We sat for like what, 40 minutes now, going from a single bin, mapping it to the learning diagram, mapping it to multiple bins, and now you tell us that the main tool we developed doesn't apply. Why doesn't it apply? Why doesn't it apply, and what can we do about it? Okay. Let me start by saying why it doesn't apply, and then we can go for what we can do about it. Okay. Now, everybody has a coin. I hope the online audience have a coin ready. I'd like to ask you to take the coin out and flip it, let's say, 5 times, and record what happens. Okay? And when you are at home, flip the coin 5 times. Please, if you happen to get all 5 heads in your experiment, then text us that you got all 5 heads. If you get anything else, don't bother text us. Okay? We just want to know if someone will get 5 heads. Okay? Everybody's done flipping the coin? Okay? Because you have been so generous and cooperative, you can keep the coin. Okay? Okay, now, did anybody get 5 heads? All 5 heads? Okay. Congratulations, sir. You have a biased coin, right? We just argued that in sample corresponds to out of sample, and we have this Hövding thing, and therefore if you get 5 heads, it must be that this coin gives you heads. Okay? We know better. So in the online audience, what happened?
Yeah, in the online audience is also 5 heads.
There are lots of biased coins out there. Okay? Are there really biased coins? Okay? No. What is the deal here? So let's look at here. Here I can, with the audience here, I didn't want to push my luck with 10 coins because it's a live broadcast. So I said 5 will work, okay? For the analytical example, let's take 10 coins, okay? Let's say you have a fair coin, which every coin is, okay? You have a fair coin, and you toss it 10 times. What is the probability that you will get all 10 heads? Pretty easy, 1/2 times 1/2, 10 times, and that will give you about 1 in 1,000. No chance that you will get it, okay? Okay, no chance, but very little chance. Okay, now the second question is the one we actually ran the experiment for. If you toss 1,000 fair coins, it wasn't 1,000 here, it's how many there, maybe out there is 1,000, okay? What is the probability that some coin will give you all 10 heads? Not difficult at all to compute. And when you get the answer will be, it's actually more likely than not. Okay? So now, it means that the 10 heads in this case are no indication at all of the real probability. That is the game we are playing. Can I look at the sample and infer something about the real probability? No. In this case, you will get 10 heads, and the coin is fair. Why did this happen? This happened because you try too hard. Eventually, what will happen is, okay, Hövding applies to any one of them, okay? So, but there is a probability, let's say, 0.5% that you'll be off here. Another 0.5% that you'll be off here. If you do it often enough, and you are lucky enough that the 0.5% are disjoint, you will end up with extremely high probability that something bad will happen somewhere. That's the key. So let's translate this into the learning situation. So here are your coins, okay? And how do they correspond to the bins? Well, it's a binary experiment, whether you are picking a red marble or a green marble, or you are flipping a coin getting heads or tails. It's a binary situation, so there is a direct correspondence. Just get the probability of heads being mu, which is the probability of a red marble corresponding to them. So because the coins are fair, actually all the bins in this case are half red, half green. Okay? That's really bad news for a hypothesis. The hypothesis is completely random. Half the time it agrees with the target function, half the time it disagrees. No information at all, okay? Now you apply the learning paradigm we mentioned, and you say, okay, let me generate a sample from the first hypothesis. I get this, I look at it, and I don't like that. It has some reds. I want really a clean hypothesis that performs perfectly, all green, okay? You move on, and okay, this one, even, I don't know, this is even worse, okay? You go on and on and on and on, and eventually, lo and behold, I have all greens. Bingo! I have the perfect hypothesis. I'm going to report this to my customer, and if my customer is in financial forecasting, we are going to beat the stock market and make a lot of money, and you start thinking about the car you are going to buy and all of that, okay? Well, is it bingo? No, it isn't. And that is the problem. So now we have to find something that makes us deal with multiple bins properly. Hefting inequality, if you have one experiment, it has a guarantee. The guarantee gets terribly diluted as you go. And we want to know exactly how the dilution goes. So here is a simple solution, okay? This is a mathematical slide. I'll do it step by step. There is absolutely nothing mysterious about it. Okay.